Welcome back. We've discussed how satellites get electrical power and how they communicate with Earth. And in this segment, we will focus on an additional payload component needed for satellites whose primary goal is to take pictures: cameras. So cameras on board satellites are similar and in some cases identical to the camera in a cell phone. If a satellite's camera is pointed away from Earth, typically it's doing astronomy, so taking pictures to study other planets or stars or galaxies. If a camera is pointed towards Earth, there's a wide variety of things to do. So taking images for weather forecasting, monitoring for hazards, or like straight up spying on other countries. And at least for the first two cases, imaging the Earth from a satellite is called remote sensing. Remote sensing means getting information about the Earth without actually being on Earth. And in all of these cases, we need a camera in order to take pictures. So in this segment, I want to explain how cameras work. And to be clear, we are talking about digital cameras. For those of us who can remember film cameras, there are stories of spy satellites from the 1960s and 70s that actually used film cameras in orbit and then somehow sent the film in a canister back to Earth where it was collected and developed. That's like totally wild. But it's been a long time since I've even seen a film-based camera. So in this segment, digital cameras in space. To figure out how a digital camera works, let's first look closely at images from two different satellites in low Earth orbit. The first image is from a camera on board the Hubble Space Telescope. The image is of a nearby spiral galaxy, and all of those bluish regions scattered throughout the galaxy are areas where new stars are forming. But as we zoom in, you'll notice that what looked like a continuous smooth image starts to get pixelated. And as we get really close, each box or pixel contains a single color. So let's look at a second image. This image is also taken by a satellite in low Earth orbit, but this time the camera is pointed towards Earth. The satellite that took this image is part of a network of low Earth satellites run by a company called Planet. Planet provides Earth imaging, remote sensing, for a variety of purposes. And it's actually kind of fun to go to their gallery and scroll through their public images. This image is from that gallery and was taken above the rocket launch pads at Cape Canaveral, Florida. You can see the Florida coastline on one side of the image, and in the middle is one of the SpaceX launch pads seen from above. However, as we zoom in on the launch complex, it again becomes pixelated, with each pixel containing a single color. These pixels are an important clue to how digital cameras work. The images taken by a camera on a satellite or from your phone use the same technology and often some of the same components. If you take your phone apart, and I don't recommend it, but if you did, behind the camera opening, you'll find a series of tiny lenses which collect and focus the light onto a small detector. The detector is made out of a material that is sensitive to light. For your phone and many satellite cameras, the detector is made out of silicon. Silicon detectors are sensitive to optical light that our eyes see. When light hits a silicon detector, that light generates an electron, which can be collected and counted. Now, this should sound familiar to solar panels that we discussed a few segments ago. Light hits a solar panel and generates electricity, which is actually just a bunch of electrons. And it's true, solar panels and digital cameras are similar, and the key difference is that when light hits a solar panel, we don't know where it hits. That is, we lose the positional information. Light hitting one side of the solar panel is the same as light hitting the other side. For a digital camera, the region that is sensitive to light is divided into a superfine grid. Each region in this grid is called a pixel. Each pixel has its own electronics so that we can count how much light has hit that pixel independently. Imagine like each pixel is a measuring cup, and the grid of pixels on a detector is like thousands or millions of measuring cups neatly packed up all together. As light or photons rain down on this grid, we can read off how much each cup has been filled. That is, how much light has fallen onto each pixel. And this is a number. For each pixel, I have a single number representing how much light has hit the detector in that spot during the time that the image was taken. From these numbers, I can build up an image. It's kind of like paint by numbers. Each pixel has a single number, but by zooming out, it creates what looks like a continuous image. The images that we examined a few minutes ago have millions of pixels. So, to represent my image, I need millions of numbers. And numbers are something that we can store in a computer. Numbers are also something we can transmit wirelessly or using the radio transmitters, receivers on a satellite, as we talked about last segment. If a satellite takes an image, it can transmit a series of numbers. A ground station can receive those numbers and rearrange them to reconstruct the original image. And this process of sending or receiving images is the same whether you're texting a picture to a friend or sending an image from the Hubble Space Telescope back to Earth. Silicon detectors are sensitive to optical light, but it's also interesting to take images at wavelengths that are not optical. Infrared cameras work the same way as optical cameras, but the silicon detector is replaced with a different kind of material. Usually it's a composite of things like mercury and cadmium or indium. These materials are sensitive to infrared light, which has less energy or longer wavelengths than optical. Infrared cameras are particularly good at sensing temperature differences, and this leads to some interesting remote sensing applications. So, for example, infrared images can more easily detect and monitor forest fires or lava flows as compared to an optical image since they can see temperature differences. In more urban environments, infrared images can be used to estimate energy efficiency or heat sinks in a city. For weather forecasting, combining both optical and infrared imaging provides a much more complete picture of cloud layers and the temperature gradients in the atmosphere, which in turn means better forecasting. All these applications are passive observations, using the illumination from the sun or heat given off by an object to take a picture. There are also active observations that can happen from satellites, things like radar or LiDAR. Radar observations actively illuminate the source with light at radio wavelengths and receive the signal back to build up an image. So coming back to a graphic we've seen before, the electromagnetic spectrum, there are cameras designed to take images at nearly every region of the spectrum. Satellites often have multiple different cameras for different wavelength regimes, and in some cases might combine passive and active remote sensing. Okay, let's put everything together that we've discussed about payload components and look closely at an example satellite. Since I've already brought it up, let's take a look at the Hubble Space Telescope. This is an image of Hubble in orbit, and while we've seen this image several times, we can now identify individual components. So the solar panels provide all the electrical power to the satellite, and these can be swiveled relative to the body of this telescope to keep them pointed towards the sun. We can also see a communications antenna. That's where Hubble transmits its data back to Earth. And there is a separate, smaller antenna where it receives instructions from Earth. If we fade into a schematic of the satellite, we can still see these components, but we can also see the suite of cameras which allow Hubble to do its amazing science. Hubble has many different cameras for different kinds of science. So there are 2 optical cameras that take images, 2 optical spectrographs, which split the optical light into individual wavelengths, and 1 infrared camera. And these cameras are dear to my heart, as much of my career has been analyzing images from digital cameras, both from the Hubble, James Webb Space Telescope, and other space and ground-based systems. Okay, we've now discussed the major payload components on a satellite. We next need to ensure that these exquisite systems, which we build here on Earth, can both survive the launch into space and can operate in that harsh space environment. And rather than leave this to chance, in the next segment we'll discuss the payload testing that's done to ensure that our cameras and the rest of the payload actually work once we get into orbit.